Hello, it's Dr. Daystorms, and this video is going to cover how we determine the geometry of larger molecules. So now we have more than one central atom per se. And rather than discussing the shape of the entire molecule, we want to break it up into its little pieces and always think about the shape of each individual central atom. So let's just look at an example. One of the problems that people tend to have whenever they draw Lewis structures, and first of all, please make sure that you get used to drawing out Lewis structures and always check for formal charge. This one is of acetic acid, which is the main component of vinegar, and it's already been drawn for you. But people make the mistake that when they see this, they would just assume, hey, this is linear because of the way the Lewis structure is drawn. But you have to realize that a Lewis structure is a two-dimensional representation of a three-dimensional object. So how do we go about doing this? So for these larger molecules, what you want to do is break it apart with each of the individual atoms. So let's first take that carbon. When you draw it, you have to look to see how many electron domains it has. It has 4 electron domains, and all 4 are bonds, so none of them are lone pair electrons. So therefore, when we look at that, the electron domain geometry is tetrahedral. That's also the molecular geometry because there are no lone pair electrons. And so, even though it may look like it's 90 degrees, the angle between the hydrogen and the carbon, because you have to realize that that's between this point, and this point, that angle is going to be 109.5 degrees. So let's look at another part. This time, let's move over to this carbon. Okay, so let's redraw it. I'm just going to draw that part of the carbon. Okay, now if we look at this, we have to count the number of electron domains. We have 1, 2, 3 electron domains. So knowing what we know about the electron domain geometry, since it's 3, it's going to be trigonal planar. Now, is the molecular geometry the same as the electron domain geometry? And for this carbon, it is yes, because around that carbon there are no lone pair electrons. So the two are one and the same. So in an ideal world, the angle made up by this carbon to this oxygen, that angle would be 120 degrees if it's trigonal planar. However, because we have the presence of double bonds, it pushes down on the bond between the carbon and the carbon and the carbon and the other oxygen. And so it's going to be slightly less than 120. I don't require you to know the actual number, but just know it's going to be slightly less than 120. Likewise, the angle from here, okay, the angle from here to here, for example, would be a little greater than 120 because of the fact that the double bond is pushing down to maximize the repulsion. Finally, let's go ahead and look at the oxygen. I'm going to redraw just the oxygen. It's got 2 sets of lone pair electrons, a hydrogen, and then it's attached to that carbon. So how many electron domains are there? There's 1, 2, 3, 4. So the electron domain geometry is tetrahedral. But the molecular geometry is different, and that's because 2 of the electron domains are made up of lone pair electrons, so they don't count. So the actual molecular geometry around that is going to be bent, similar to what we see with water. Now we can actually get an idea if, remember, the angle is actually based off of the electron domain geometry. So if this was a perfect tetrahedral, it would be 109.5. However, because of the lone pair electrons here, they are pushing down on that bond, and so it's going to be a little less than 109.5. So here we're looking at two different models of the same thing, but we can clearly see the geometry and how you can have the geometry of the tetrahedral, the trigonal planar, and the bent all within the same molecule. And also, we can see here what it looks like with the space-filling molecule. Or space-filling model, I should say. Hopefully this has helped you realize that you can break apart these larger molecules and talk about each individual section as its own shape. I'll see you in class.